Good afternoon, everyone. Let's see, homework is due tonight. Hopefully, all of you have had good luck with that. So today we will finish the first chapter on probability, and then we'll start discussing random variables, some of the basic ideas of random variables, and in particular discrete random variables today. So what I'd like to do is start off by going back to Bayes' theorem, which we looked at last time, and just want to show a graphical technique that sometimes students would prefer instead of just using the expression for Bayes' theorem. So there's another way we could take a look at this problem. So the idea is we are interested in the probability of A given B, but we know the probability of A, the probability of B given A, and the probability of B given A complement. So we know the conditional probabilities, but in the wrong direction. We want to reverse the direction of the conditioning. And so here's our expression to calculate that. Well, let's go to our example on diagnostic testing. And so we're given these probabilities, which in the language of diagnostic testing, this is the prevalence and sensitivity of the test and the specificity of the test. So these are typically the prevalence can be attributed to just the nature of the disease and the risk group of individuals that you're looking at. The sensitivity and specificity, manufacturers, when they design diagnostic tests, have to carry out trials on patients that are known to have a disease and that are known not to have the disease. And then they measure or record how often they get positives and how often they get negatives with that. And then they can report to the physicians using the test. Well, I guess first they go to the Federal Drug Administration. They have to prove that their test does work. And so what can happen, we see here, we went through these calculations, and we see that the probability of having the disease, given the fact that the test is positive, is still pretty low. And we saw that that's because there were too many false positives. You know, most people don't have the disease, a fraction of them test positive, and that fraction overwhelms the people that have the few people that have the disease, most of whom test positive. In fact, we could even have 100% sensitivity here and still get about the same thing. That is, every person with the disease tests positive. But still, if you look just at the positives, most of those people don't have the disease. And that's due to the calculations we did with Bayes' theorem. So one thing that this points out are you actually have to do the calculations. You can't just use your intuition to think, well, if this is the sensitivity, this is the specificity, the test has to really have a high positive predictive value. It just doesn't happen. You actually have to do the calculations, and sometimes you get results that don't seem like it coincides with what you thought it would ahead of time. Okay, so one way of doing this calculation is, let me get rid of the ink, and we'll go to the smart board. And I will take a picture of just okay, so we want to make use of these probabilities. Well, one way of doing this is to use what's called a tree diagram. And so we start out with the event that we know the unconditional probability of. And so we have a branch for D and for D complement. Then we can go out, given, okay, actually, let me go here to D. Let me just delete that. Start there. And D complement. And then you have T plus, T minus, T plus, T minus. So in the tree diagram, we have these. We have the event either having the disease or not. That's at the first stage. And so we get the probability 0.001, 0.999. And then of those that have the disease, we will put down the conditional probability of T plus given D. That's 0.95. And so the other conditional probability has to be 0.05. And similarly, the probability of T minus given D complement is 0.9. And so that says the complement of that is testing positive, has to be 1 minus 0.9 or 0.1. So we can get the probability of D intersect T plus just by multiplying. So that's going to be 0.001 times 0.95. So we can get the probability of each of these branches, which is the conditional probability. And what we're interested in is the probability of D given T plus. And let me show, so in red, okay, well, we need to find the probability of D intersect T plus divided by the probability of T plus. So to get the probability of T plus, we need to add this probability for that branch because it's T plus there, and then the probability for this branch. And then in the numerator, we have this probability, for this top branch up here. So using the tree diagram, essentially Bayes' theorem says that you take the branch of interest, that intersection, you have the probability here by multiplication, and then in the denominator you have to look at all the branches where we have T plus. So it could be that instead of just disease and disease complement, we have maybe a mild case of the disease as well. And that could be, we could have as many branches at the first part as one might is needed. And so a tree diagram is another useful way of working a Bayes' theorem problem. So here we have unconditional probabilities. Then each step here, we have conditional probabilities. And then you can go out further, more complex experiments. The tree can go out further and further, where each stage we have conditional probabilities given the branch that you're on. Okay, now in that previous example, the probability of testing positive depended on whether or not you had the disease. It changed an awful lot there. Now, sometimes that probability doesn't depend, a probability of one event doesn't depend at all on the other event. And that leads us to what we call independent events. So there are a couple ways we could define it. The basic definition is that the probability of the intersection is equal to the probability of A times the probability of B. Now, in general, the probability of the intersection has to follow the multiplication rule, and it has to equal both of these two quantities here. And so the probability of A intersect B is equal to this, is equal to this as well. Now, But if they're independent, then we get rid of the conditional probabilities in the equality, and we just, it makes for a simpler calculation. Now, if probability of B is greater than 0, what we do is we can look at this last expression, and if we divide both sides of this by the okay, so we look at this, we divide both sides by the probability of B, and that gives us a conditional probability on the left. So we divide by probability of B, divide by the probability of B. This is the conditional probability on the left-hand side, and on the right-hand side, the probability of B cancels out. And so we get the unconditional probability of A given, or the conditional probability of A given B is just equal to the probability of A. Similarly, if the probability of A is greater than 0, the conditional probability of B given A equals the probability of B. So that says that when we have the events having non-zero probability, they're independent if and only if the unconditional probability is the same as the conditional. So this says if you know B has occurred, it doesn't change what you think the probability of A is. It's the same as the unconditional probability. So what this says then is that in a certain sense, independence means that A does not affect B and vice versa. Okay, now, independence is something that if you have A and B defined through some experiment, you have to check for independence, using the way that A and B are defined. Now, sometimes in forming a model, we just assume A and B are independent. So hopefully that assumption is justified in the way that the real world behaves. Now, there were, I think it was the Space Shuttle Challenger disaster. There was an engineering study where they tried to calculate the probability of a failure. And they had a chain of events, and they made the assumption of independence. And what that does is you multiply all the probabilities and you get your final probability. But it turns out that in that chain there were events that were not independent. That is, if one event happened, it would make the other one more likely to occur. And so that calculation, just by multiplication of the probabilities, is not necessarily going to be anywhere near correct. So if you make use of independence in doing an engineering calculation, you need to make sure that in the real world, these two things are independent. If they're not, then your calculation isn't going to be too useful. Okay, now if we have more than two events, then we've got several ways we could have products of probabilities. And so mutual independence, and we'll just, instead of using the word mutual, we'll just say simply independent, is if we have A1 through AK, so we have K events. And so if we pick any subset of them, M might be 2 or 3 or 4, that we have the multiplication. The probability of the intersection is the product of the probabilities. So for instance, if we have 3 events, A, B, and C, then to have those 3 be mutually independent, we need all of the two-way intersections to satisfy the independence. That is, the probability of A intersect B equals the product of the probability of A times probability of B. That has to be true for A and C, and B intersects C. And then the three-way intersection also has to satisfy the product rule. The probability of the three-way intersection equals that. So if you have 4 events, then you've got all the pairs, all the 3 groups of 3, and the 4-way has to satisfy it. and so on. So mutual independence, there are a lot of things to check. But if you assume it, then you have a lot of things going for you. Okay, now sometimes, and as you'll find out on homework, you can have events that are pairwise independent, but not mutually independent. So if you have independence, that implies pairwise independence, but you could have pairwise independence, that is, this is satisfied, but the three-way intersection property is not satisfied. And so on one of the, in your current on homework 2, you'll work a problem where that's the case. Okay, in engineering applications, often independence is assumed when you have several components and you want to calculate the probability that a system is going to work or is going to fail. And so we'll look at some components that are connected in parallel and some that are connected in series, and we'll try to calculate the probability that the system works. Okay, so first of all, let's look at system A. And we see that this diagram says that they are in parallel. So if we can get from the left to the right of the diagram, the system will be working. And we can get through either if one is working or if two is working. They don't have to both be working. All we need is one path across. So 1 and 2 are connected in parallel. Okay, now if we go down to subsystem B, we see that to get from left to right, we have to go through both 3 and 4. And so that's what we call a series, a system connected in series. And that subsystem will work only if both of them work. So let's see if we can figure out the probability that this system will work. Well, first of all, okay, so let's let CI be the event that component I works. Okay, now you can also work the problem in terms of failure. And it's done using kind of similar arguments, but you're looking at the probability that a component fails throughout. So I like to be more optimistic and think things are going to work. Okay, so if we're in parallel, the system works if one or the other work. So we have the union, C1 union C2 will be the probability that system A works. Now to use, typically we assume that components are independent to do the calculation. If they're not independent, then you have to do the calculations of intersections using conditional probabilities. But we'll make the assumption these components are independent of each other. Okay, so it's easier to check if or find the probability of the intersection. Now, if C1 and C2 are independent, that implies C1 complement, C2 complement are independent. Now, I can't remember if I gave you a homework problem proving that. If I didn't, what you should do is be skeptical of that fact and go home and prove it to yourself tonight. Right? You're all going to do that. Actually, you won't even wait till tonight. Right after class, you'll prove that they're independent. But that is a homework problem that I've given in the past. I don't remember if I gave it on this current homework. But if you have independent events and their complements are independent of each other, and actually C1 would be independent of C2 complement, and so forth. Okay, so by independence, we get, so independence will give us that the probability of the intersection is equal to the product of the probabilities. And then we make use of the fact that the probability of the complement is 1 minus the probability of the original event. So in terms of the original event, the probability that the system works is 1 minus P of C1, 1 minus P of C2. So if we have, if these are the same value and you let it just equal a number, then it's really easy to do the calculation. And that's on your homework, I think you'll have each of these being a probability P. All of them fail with the same probability or work with the same probability. Now, system B works, since it's in series, both of them have to work. So we need to find the probability of the intersection of C3 and C4. So, so in terms of the intersection, we just use independence and get the probability of C3 times the probability of C4. Okay, now if we next would probably want to go to the whole thing. So to do that, we need to use the fact that A and B are in parallel. So what we have is the probability the whole thing works. So actually, let me go back to the whiteboard and capture this. Okay, so what we've got is, we need the probability the whole thing works. So this is really technical language. I should have, okay. So that's going, okay, so let me call this event A if system A works. We'll call that B if system B works. So the whole thing will work if either system A or system B will work. Well, that's going to be 1 minus the probability of A complement intersect B complement. So we get 1 minus probability of A complement times the probability of B complement. And finally, we get 1 minus the probability of A times 1 minus the probability of B, just as we have up there. And so we would have to substitute in this for the probability of A and this for the probability of B. So you see, we probably will get some cancellation out of this. Some of the ones will cancel out, but it ends up being a fairly long expression. But it's going to simplify somewhat if all the probabilities were the same. If I could set P1, P of C1 equal P of C2 equal P of C3 equal P of C4. In that case, it will simplify somewhat. So essentially, you can work very complex diagrams like this by finding the probabilities of each of the parallel branches, and then using, and then if they're in parallel, you find the probability they don't work using the fact that, using the properties of intersections and their probabilities. Okay, any questions then on probability? So now what we will do is to move on to looking at random variables. Okay, so we're going to be making use of probability throughout the whole course. Now, random variables will enable us to give numbers to outcomes, and then we'll be able to give probabilities to those numbers that we associate with different outcomes. So we're just essentially applying probability theory to real numbers or to integers and so forth throughout this chapter. Now, random variables will be our link between probability and statistics. See, in using statistics, we carry out an experiment and observe a collection of numbers. And what we'd like to do is to say something about the properties of the experiment based upon that collection of numbers. So we want to carry out statistical inference. Now, before we can do that, we need to look at those possible outcomes of the experiment, and random variables will give us models that will lead to the numbers and give us, or the numbers as the result of the experiment, and give us a probability structure for those numbers that depends on the nature of the experiment. Okay, so first of all, we'll give a fairly abstract definition of random variable. Then we'll look at some fairly concrete examples, and then we'll develop some of the most commonly used distributions for random variables. Okay, so essentially what we have is a sample space S, and random variable is just a function from S to the real line. So if this is our sample space, and this is the real line, for each point in the sample space, a random variable just gives us a real number. So if this is S1, S2, S3, then this point on the sample space would be x of S1, or S3, that's x of S1, x of S2. So you know, we have this experiment, results in some kind of outcome, and then the random variable just gives us a number for each of those outcomes. Now, the probability structure is associated with this sample space S. So which outcome occurs, S1, S2, S3, etc., is random. There's a probability for each. What that tells us then is the number that we observe in the end, the x of S1 or x of S2 and so forth, is also going to have a probability associated with it. And so we'll look and we'll develop the probability structure on a real line based upon the probability structure and the nature of the map X that takes the sample space into the real line. Okay, so our use of the capital X is similar to what mathematicians do with an F in math classes. The most common notation for a function is little f. And then f of x is the value of f when we apply the function f to the number x. And so f of x is just a number that we associate with x. Often we let little y equal f of x. So y is just another number that f maps x into. Well, for us, we have capital X, and our point in the sample space, x of s, is a number that the random variable associates with the outcome s. And so that corresponds to f of x. Now, if we just want to denote a value that x takes on, we'll often use little x for a number in the real line that has been associated with the little s. Okay, so here's an experiment, very simple one. We toss a coin 4 times, and we record head or tails for each of the tosses. So if we look at this, there are going to be 16 possible sequences going from tail, 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 tail to head, 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 head. And so here I've written down the possible sequences. Now, a random variable can be anything that gives me a number for each of those sequences. So I could let x be the number of heads. I could let x be the number of tails. I could let x be the difference. And so a random variable is just something that gives me a number for each of those sequences. It could be something really trivial, like it's always equal to 15, no matter which outcome I get. But then that random variable is not very interesting because it's constant. Okay, so what I'm defining here for my random variable x is the number of heads until the first tail. So for instance, if I have heads, tails, I have one head before the first tail. Now, if I have a tail on the first toss, that gives me a 0. There are no heads before the first tail. So all of these 8 outcomes on the first 2 lines, which have a tail on the first toss, will have 0 as my value of x. Then I could get a head on the first toss and a tail on the second. So in these 4 outcomes, 4 possible sequences, I have a head followed by a tail, so my number of heads is 1. The next 2, I have heads, heads, and then tail. So I have 2 heads before the first tail. And then here I have 3 heads before the first tail. And I don't know how many heads I would have, but since I only flipped, I never did get a first tail. So I'll just define that the value of x is 4, because it's going to be at least 4 heads before I get a tail. I could keep flipping, have 5 heads, 6 heads, 7 heads, but since I stopped, 4 is the value that I have. Okay, the reason I picked this is that you can see that the different values that we take on are associated with different numbers of outcomes. Okay, now what we're going to be interested in is, well, what's the probability of observing a 1, or a 2, or a 0, or a 4? And what we'll do is make use of the fact that if we have a fair coin, we can get a probability for each of those sequences, and then we can add up those probabilities of all the sequences that give us a certain value of our random variable x. Okay, so in symbols, let's first do that, then we'll go back to our, well, actually, let's just take a look at this a little bit more. Okay, so let's suppose we want to look at x equals 1. So what is the probability that x is equal to 1? Well, it's going to be the probability of the collection of outcomes h, t, 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 h, t, t, h, h, t, h, t, and h, t, h, h. Okay, so what our definition will do is say, well, what's probability x equals 1? Well, it's going to be the probability of all the outcomes in the sample space for which x is equal to 1. And so I put that in my collection here. Each of these is going to have probability 1/16, so I can use the fact that I have 4 outcomes in my event. Each of those has the same probability 1/16 because I'm tossing a fair coin. We have to make some assumption about the coin before we can calculate the probability, but we'll assume it's a fair coin. And so I get 4/16 is the probability that x is equal to 1. Okay, so what I've done in symbols then, so A is some subset of the real numbers. Well, A was just a single value 1. And then the probability that x takes a value in A is just the probability of the set of outcomes in the sample space that are mapped into that event A. And so if we can define this for any subset A of a real line, we'll get the probability distribution of X. And so what I just looked at, the probability that X equals X, was shorthand for the notation, or for probability that X takes a value in the set consisting only of little x. Okay, so if we go back to our experiment in example 12, we assume that we have a fair coin, then each outcome has probability 1/16. So this is what we just looked at. The probability that x equals 1 is 4/16, or 0.25. If we go back and look at, well, the zeros are these 8 outcomes, so that's going to be 1/2. 2 has 2 outcomes. 3 and 4 each have 1 possible outcome. So putting that together, the probability that x equals 0 is 0.5. Probability x equals 2 is 0.125, 1/8. And then we have 1/16 for 3 and 4. And when you have a random variable like this, we only need to specify the probabilities for the values that can actually occur. Everything else has probability 0. So, so when we make a table like this, okay, so all other values of x have probability that x equals little x is equal to 0. So there's no way of getting a -1 or a 1.5 or pi or any other number. These are the only possible values that we have. Now we can use, okay, so this is what we're going to be calling the probability distribution of the random variable x. And once we've specified this, we can find any probability of interest concerning the random variable x. The idea is, once we get, if we're interested in probabilities of the random variable x, once we've found this function, we don't have to go back to the original sample space. We just can use this function here to calculate, like if I want to find the probability x is 2 or more, I don't have to go back to the original sample space. I just look at the probability of 2 plus the probability of 3 plus the probability of 4. So we'll come back to looking at this sort of function when we have just a finite or countable set of values. That will give us one type of random variable, and we'll spend, which is called a discrete random variable. And after I make a few more comments, we'll go back to that and look at some commonly used discrete random variables. So there are 2 main types of random variables that we can look at. The one we just saw is discrete, the other is continuous. So a random variable is a mapping x from S to some subset of the real numbers. So the domain is where we start the mapping, is S, and the range we'll just call R of x. Now if the range is countable, then x is a discrete random variable. Okay, or finite is countable. So if it's finite, it's a discrete random variable. So in our example, the range of x was 0, 1, 2, 3, and 4. Now, in some cases, R of x will not be countable, in which case we're going to be using what is called a continuous random variable for x. And usually for the variables we'll look at, the range of x is usually going to be an interval of some sort. It might be from an infinite interval that goes out to infinity, or it might be over some finite range, like from 0 to 1. It could be a union of disjoint intervals, but that's not very often of practical interest. Now, when S is countable, X has to be discrete. And if S is uncountable, the sample space, it could either be discrete or continuous. So you could, if the final set of values is only finite, then we have to have a discrete random variable. Okay, now what I found earlier was the probability of each different value of X. And that function is what we're going to be using in general, and so we'll call it a probability function, or I like to use probability mass function, which tells us that the different values in the range have a probability or a mass to each of them. And we define that as by giving the probability that X equals X for every real number. And so what you'll have are a countable number of X's where that is bigger than 0, and most X's, the rest of the real line, will have probability of 0. So in the previous example, we had a positive value for X equals 0, X equals 1, 2, 3, and 4, and everything else, like 3 halves or 5 or 26 or whatever, had probability 0. So for a discrete random variable, the range is going to be a at most countable sequence of X's. So we had 0, 1, 2, 3, 4 in our previous example. Some random variables have, if I said, well, what's the number of heads before the first tail, and I keep flipping until I get a tail, well, I could go on forever. So any positive or finite or any positive integer could be the value, in which case we would have a countably infinite set here. So the range of X is equal to X1, X2, and so forth. So if we add up these probabilities, we have to get 1. So the total, the probability of the sample space is equal to 1, just by definition of the sample space. So since the random variable takes each point in the sample space to somewhere on the real line, the total probability of the real line also has to be 1. And since the R of X are the only values on the real line that we observe, the total probability of the range of X has to be 1. Now, if we take so in general, to define a probability distribution, we have to be able to find the probability that X is in any subset A of real numbers. And what we'll do is add up the probabilities of every X in A that's part of this range. If it's not part of this range, it just has probability 0. So the only X values whose probability we need are those that are in A and also in the range of X. So for instance, in our example, let's suppose A is equal to the interval from minus infinity to 2. And I'll include 2. So the probability that X is in A is equal to the probability of A, which is minus infinity, comma 2, intersect the set 0, 1, 2, 3, and 4. Okay, so my range of X was 0, 1, 2, 3, and 4. So the intersection of that is just going to be the set 0, 1, and 2, because 3 and 4 are not in A, 0, 1, and 2 are in A, And so I would have the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. So that will give me the probability that x is in the set from minus infinity to 2. And for notation, often I'll write that as the probability that minus infinity is less than x is less than or equal to 2. Okay, let's go to the dice experiment, and we'll assume that we have fair dice. We toss the pair of dice, and we can get outcomes 1, 1, 1, 2, up through 1, 6, and then 6, 1, 6, 2, up through 6, 6. So there are 36 different outcomes here. And if the dice are fair, the probability is exactly the same for all of them. So for any pair I and j, we get probability 136 for the ordered sequence of numbers. Now, the most common random variable defined on tossing dice is the sum, or the total spots showing. That's because many gambling games involve using that. I don't know of anybody ever play games where you look at the minimum or the difference or the maximum? Okay, but but there are many random variables you could define on this sample space, and this just happens to be one. So we can compute the probability mass function for x using probabilities of 136 on the original sample space. So we look at each possible value of the sum. For instance, what's the probability that x equals 6? We can have a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, a 5 and a 1. Those are the only ways that we can get a 6. There are 5 of them, so we get probability 5 over 36. And later we're going to use this, we'll use a function little p with the subscript indicating the random variable and the value of 6 to indicate or to be the same as writing the probability that x equals 6. Okay, so to find the probability mass function then of this random variable, we have to do this for all the possible values, 2, 3, 4, up through 12. And if after we do that, we could draw a graph of it, looking on the next page, and we see like here's 6, that's 5 out of 36. Probability of the 7 is 6 out of 36. Probability of the 2 is 1 out of 36. Similarly, probability of 12 is 1 out of 36. So for discrete random variables, often we'll draw a bar chart like this showing the probabilities. It shows us the most likely value is a 7. The next most likely values are 6 and 8, and so forth. So if we're interested, so we can use that then to find probabilities of different events. So for instance, let's let A be the event that x is less than or equal to 4. And we're interested in the probability that x is in A. So similar to what I just did, the range of x is the sequence from 2 to 12. So this event A intersects R of x. 2, 3, and 4 are the only values less than or equal to 4. So we need to find the probability of the set consisting of 2, 3, and 4. Now there are a couple ways we could do this. If we go back to the original probability space, we enumerate all the outcomes that result in 2, 3, or 4. So we have 1, 1 gives us 2, 1, 2, and 2, 1 give us 3, 1, 3, 2, 2, and 3, 1 give us a 4. So there's 6 of those outcomes, so we get probability 1, 6. Now, more commonly, once we have the probability mass function, we'll just use it to calculate probabilities for x instead of going back to the original sample space. So the second approach, we just have, we have calculated the probability of 2, the probability of 3, the probability of 4. Those are these values here. We add them up and we're done. So the advantage of having the probability mass function is we no longer have to revisit the original sample space. We can calculate any probability involving x just using this probability mass function. Okay. Kind of an aside, and just to help you do at least one of the homework problems, we're going to be using in defining distributions and in other, we'll have other statistical uses of a function called an indicator function. So for any event A, an indicator function will take on the value of 1 if S is an element in A, and it will take the value 0 if S is not in it. So this is just a function telling us if an outcome S is in an event A or not. We get 1 or 0, depending on whether it's in A. So let's, I've given you a homework problem kind of like this, and so I've modified one of the problems a little bit. Let's let S be 1, 2, 3, 4, the sequence. And I'll define different indicator functions. So X is going to be the indicator of the set 1, 2. Y is the indicator of the set 2, 3. Z is the indicator of the set 3, 4. And then I can let W be a linear combination of these. So to evaluate W, I need to evaluate X, Y, and Z at each possible value. So let's start off with W of 1. Well, I plug in X of 1, Y of 1, Z of 1. And then we look, is 1 in this set X? Yes, it is. So X of 1 is equal to 1. That's what we get here. Is 1 in the set 2, 3? No, it's not. So that's where this Y of 1 is equal to 0. And finally, is 1 in the set 3, 4? And the answer is no, it's not. So Z of 1 is equal to 0. So I add these up. 1 minus 0 plus 0 is just 1. Now, if I look at 2, we see that 2 is in the set X, so I get a 1 here. 2 is in the set 2, 3 for Y, so I get a 1 for Y. But 2 is not in 3, 4, so I get a 0 there. So when I evaluate W at 2, I get 1 minus 2 plus 0, or negative 1. So we use a similar argument here for W3, W4. You check whether 3 is in 1, 2, but it is in 2, 3, and in 3, 4. So I get a 0, 1, and 1 when I substitute in, and end up with minus 1. And we do a similar argument for W4. So we'll be using the main use of indicator functions that we'll have is when we define a distribution, we want to know over what set is that dense probability mass function greater than 0. And so if we put in an indicator function for the range, that automatically becomes equal to 0 for everything outside the range. So indicator of the range is a useful way to write it as a single function. And so we'll be making use of the indicator function quite heavily in writing down distributions. Okay, so believe it or not, this is probably a good place to stop. So next time, what we'll do is look at what I could say are the greatest hits of discrete distributions. Those of you that are, you know, I grew up listening to the radio, and every week we had the top 40 biggest hits. They still do that a little bit, but I think back when I was younger, it was a bigger thing back then. And so here are the most popular discrete distributions. And so these will be probability distributions that are going to be used in statistical inference. So if you take applied courses in statistics, you're going to run into these. And so those are the primary ones I want to introduce to you. And then we'll continue, after we talk about discrete random variables, we'll introduce you to continuous random variables. Okay, so we will see you all on Friday.